Hello, welcome to this session. In this session, I'm going to be introducing you to binary search tree. So, as the name suggests, binary search tree is one of the nonlinear searching algorithm. Uh, the structure is pretty much like a traditional tree, or unlike the traditional tree, it has principle. It has principle. The principle is such that you know each node can only have two children. So in trees you have branches. There's a roots, and then roots stem up, and then you can have branches from uh, any node of the tree. But in binary search tree, the principle is that each node cannot have more than two sub branches or branches from that node, in which in this case, in this context, we call it like children. So each node can have a maximum of two. It can have less. It can have one. It can have no child at all, or but it cannot be more than two. So for us to really make sense of the binary search tree, it's important that we visualize it. So if you visualize it, you would understand a bit more. So I'm going to be showing a visual a site that you can go to check. So if you go to visualgo.net, you can also visualize any other algorithm. So I'm just going to be visualizing BST, which is binary search tree. So this is how binary search tree actually works. So we have a tree like this. So this is a node, and this is a node like that. So you notice that each of the nodes has a maximum of two children. So this is a node, which is a parent node now. This is a child of it, and this is another branch that comes off it. This is a branch from this guy. This is a branch of this one. So one principle is that a node cannot have more than two, children. Now that is one. Second is that we are talking about three nodes here: the parent and the two guys that stem up from that parent. Now all elements to the left of a node must be less than that parent. So if you look at this now, for instance, all the elements to the left of this guy are less than this parent. In this case, we have 33 here, and this is the principle that makes it efficient, and that's on the foundation in which it was built. And then all numbers that are to the right of it are more than the parent. So it's a search tree. Of course, you have to save the data that you're searching before you search them. So it's more of saving strategy for me than even the searching, as much as the searching strategy as well. So when you are inserting data, you have a strategy. Like all these ones have methods that you can use to create a node, search through the node, and insert value into the node, and all of that. So all these nodes here are created. For instance, if I'm going to insert a value now, if I'm inserting a value, it's going to be strategically saved. So if I insert a value that is more than 33, it will not save to the left, it will go and save to the right. So if I insert a number, for instance, if I call that number 44. So if I put 44 here, 44 is more than this node, so it will come to the right. So when it comes here, it compares that value with this 48. 44, is it more than 48 or not? Is less than 48, then it creates a node. In this case, there's no node existing to the left of it, so he becomes the node, the only guy to the left of this guy. If the value is more than 48, then it comes to the right. Again, it checks when it gets to a node. It checks with the node. If it is more than that node, it goes to the right. If it's less than it, it comes here. When it gets here, it compares itself to it to know where it will stay. You staying to the left or right. So numbers to the left, when it gets to that particular node, it compares itself with that node. If it is less than it, it goes to the left of it. If it is more than it, it goes to the right of it. For instance, before we go code these things. Let's say I'm inserting a number. Like I said, these are two numbers, but I want to insert just only one. Let's say I want to insert 44, like I mentioned that time. If you look at it, 44 comes here, it compares itself with that, it sees that it's more than that. When it gets here, it's less than this guy, and it goes to the right of it. If I insert a number, say 65 for instance, or 66, 66 will come to the right, it will come here. When it gets to this 61, it compares to this 61, it's still more than 61, it continues. When it gets here, it compares itself with this 68. 65 is less than 68, it won't go right, it will come left. So when it comes to this place, 65 or 66, whatever number I'm using, it is more than this one, then it comes to the right of it. If it's less than it, it goes to the left of it. So let's say, for instance, we use a non-ambiguous value. Let's say 67. You know that 67 will come here and be the right value here. So look at it. It goes 33, I'm more than you, I go to the right of it. 48, I'm more than you. 61, I'm more than you. 68, I'm less than you, I come here. 64, I'm more than you, I come to the right of it. So it goes there and saves, strategically there. So then when you're searching too, you're going to search like that. So when you're searching, you search the number I'm searching for. Is it less than this number? If it's less than this number, you're going to go to the left to search for it. So it's a strategy of saving data, such that when you're looking for data, you don't have to search everything before you get that data. You just go straight to the compartment where you feel that data will be logged based on the value of that data as it was saved. So when you save it strategically like this, it will be easy to find. Just like you see people going into maybe flying and all of that. So everybody is arranged by say. So maybe certain numbers are kept in one region, certain numbers are kept. So if you're looking for a particular person, you don't have to search through the whole plane, looking for, are you the one, are you not the one? So based on the person's number, where the region where the person is. So you just concentrate on it. And it's even easier here because you're only searching two. Is binary, and that's as the name suggests, true. You see, each of this is this. So and norm, this what we're having on the screen right now is what they call a perfect, perfect tree, where everybody have their children complete. Everybody have their children complete, and there's no one hanging like that. But I'm not going to bore you with so much of it. Sorry. Let's see how we can write a bit of this. So you can actually write it in functional notation, but I will go with the popular class notation so that you have these things here. So for some of you who are not so used to object-oriented programming, so I will explain a bit, but I will also try not to bore you with too much of explanation. So to create a class, you just use a class name class, and then you have it like this. You write your class name, unlike the variable that you name with camel case. Class naming convention, the standard in JavaScript is to use Pascal case naming. So it means that if you use the keyword class, you would be using you start your class name with a capital letter, and if there if there's another word coming, that also starts with capital letter. So it's a Pascal case for the naming convention of a class. So this is a class name. So let's say you call a class name node. I'm just explaining first of all, and then I will narrow it down to the binary search that we're talking about. I'm saying this because I know some of you are, but if you're not new to the class, you can just skip and go forward. Okay, so class is just a way of grouping an element, a related element, and the simple definition for it, you have instance of an object. Class is an instance of an object, For most people who still understand that technical, it's a bit technical, even though it's simple. But most of us have gone to school where you have your classmates, where you have a class like primary, universities, and all those things like that. So we've experienced class. That class that you experience is also the people that worked on it named this class, having that in mind. So you have a class name, whatever class, let's say class of 2022. You see that everybody in that class have something in common. You have maybe you have an education goal, you have whatever goal that binds you together, and so you have members of the class, sharing resources, sharing the same functions, and all of those things like that. And this is where the name actually comes. So you have class, you have and you define your class name. Now, so when you define a class name, the members of the class, you are going to, there's what we call a constructor or destructor. So when you have a constructor, which is the building block of that class, the building block of that class, when you instantiate a class, it's automatically, have its own, a constructor. All right, if you write constructor or not, but it makes sense for you to have a constructor, which is, the pillar of that your class. Okay, now the members of the class are instantiated through the through the constructor. Okay, they are instantiated through the constructor. So let's say we have a constructor like this. If you're writing a function, your normal function like this, where you pass in, so let's say you have a whatever function name, whatever function name that you have, if you need to pass in a param, an argument going forward, so you put param here, and then you have it like this. But your class name here, you did not have a way of passing it in like this, so it takes its own argument through the constructor. So when you instantiate a class and you need to pass in an argument to it, so this is like I said, it's a signature for this guy. So this guy didn't have this open and close brace here. So its open and close brace is actually here. This is what you have here. So whatever you pass here serves the same purpose as what you normally pass into your functions face here and there. So let's say we put in the constructor and we pass in a param, which is like this. So I just use this one to explain. And we pass in the param, and then we call that param of value. So realize when I was introducing you to this, using this as illustration, this is the value. Each of these guys have values. So when you are creating, when you create a tree, or you use the value to instantiate a tree, and then when you are saving to it, of course you're going to be getting value. So that's the value that you that signature that you have here. Okay, so by default, this dot value, this is called the members, just like your normal variables, right? So but now we use this, which refers to this context. In this case, we are talking about this node. This value is a member of this node, right? This node. So because we can have a value in another class, just like in a class where you have Juliet, in another class you also have a Juliet. So we can say Juliet of class 1, a Juliet of class 2, right? So when you are inside a class 1, you say this Juliet, right? So we have this value equals to this param that we have here, right? So and then when we instantiate a node, by default what we have to the left of it will be empty, and what we'll have to the right of it will be empty when you create a new node entirely, right? So let's say we instantiate left, and we say left is null, nothing is there yet. and then this dot's right is equally null. Okay, so you've got that. This is a node, right? Each of these guy here are nodes. These are nodes, right? So you have, let's say this guy is the first node here. So when this 44 is passed initially, it doesn't have to the left, it doesn't have to the right. On the second value comes, when the second value comes, based on the value of the second value, that will influence which direction is going. If it is less than 44, remember, it goes to the left. If it is more than 44, then it comes to the right. So if this is the node, which is this. We have just created a class for that. Okay, so the next thing I'm going to do is to write the binary search tree class itself. So here I'll come create a class. Let's say I call it binary search tree. Okay, all right. So the binary search tree, similarly, I have a constructor for it as well, but in this instance is parameterless constructor. All right. So I just instantiate a member, and I'll call it roots, which will be equal to null. So by default, no roots. All right. So this is the roots. For every 3, there must be a root. That is your origin. So for every u, there is where you come from. So by default, when you instantiate a binary search tree, you instantiate it to be null, or you can pass value into it. So when you pass value into it, that value becomes the root, and then that value begins to serves as the origin where every other data comes from. So we instantiate it to be a null, and then the next thing we're now going to do is to write some functions inside this class here. So for every class, sometimes you have a member which could just be a participating member, or a member can also be what those participating members do. For instance, a member of the class, let's say for instance a member of class is a teacher, and a member, that teacher teaches. That's the function that he does. That teaching that he does is also part of that class. So all this member that you have here, so the functions that they perform, that functions that will be performed on those members are also member of this of the class. So now, usually, traditionally, if you're writing it without a class, we would you're using, maybe you use your function keyword to define a function, a function. In this instance, if you're defining that function inside a class, there's no need for you to write a function keyword. You just go straight and write your function name. So let's say I'm I'll write a number of functions, but let's start with insert. So let's say I want to insert, so I just go straight and write insert data. So this comes with this. Usually, if this is not, you would have written something like function, and then you have it like this. But in this case, it's wrong to do that. It's wrong to do that because you are inside this guy, and then so you just go straight ahead and put this guy. And function inside a class has a traditional name called method. So when someone says what is a method, of course it's a function inside a class. So let's say we have a class, a method or functions called insert, and then we're inserting, of course, data. Okay, so just be visualizing what you have, what we did here. This is what we're trying to do now. We're going to insert data. So the data we're inserting, the value we're inserting is this 88. All right, so if there's nothing existing, it becomes a root. If something exists, it compares itself with what is existing, so that it knows which direction to go, whether to go left or to go right. So that is what we're about to write now. So we're going to get that insert function. Now, insert function, let's say insert function is going to get there and say, okay, is there a node yet? No, there's no node. And so let's say we have new node, which is equals to the instance of this node. We've created this guy as a node, which represents each of these very node that you got here. Each of these very node that you got here. So you say let new node be equals to new node. So this is one thing that you also need to know in class instances. So this is an object that we are creating now, so this guy, you can call it when you call your function. When you write your normal function, you just say let something and then you call that function. But when you're calling a class, you knew it, you're creating a new class, and this is called an instance of the class. So what you have created here will be an object. So we say new node, so you don't have to really new node, and the value you pass in, it takes the value through its constructor, right? So the value you pass in represents the, so let's say we have the data as the value. Okay, that is the new node. All right, so our next task is to then check if any node exists at all, if there's any root at all. If there's no root, then that value that is passed in becomes a root value, the root node. But if there's a value existing, then we have to compare what we are passing with the existing value and then say it should go to the right or say it should go to the left. Something as simple as that. So this one is just an instance so that we declare it as global, so we can reassign it, assign and reassign it without having to just take advantage of global declaration. Nothing much we have done yet. So the next thing is to check if there is an existing root. Check if there's a father on the ground. So just like someone moving into a new village, you have to check if there's already a king so that you can make yourself a king. Check if there's an existing root. So we say if this root, we instantiate it as null. It means that if it is null, there's no root already. So if this root is equals to null, all right, if this root is null, then we have this root would be the value that we just have, right, which is this. You know that a node is not just the value, it is a node which contains the value. Each node contains a value, all right, and that's what we have created here. Each node contains a value. So here, if the root is null, then this root becomes this first node here, new node. That's the first thing we do, when we are inserting the data. If this is this, then we'll insert that. Otherwise, S, check which direction to go. That's the next thing. Check which direction to go. If the root is null, there's a value, then you now compare the data that you have with that value. If that data is less than that value, then it goes to the left of it. If it's less than it, it goes to the left of it. If it is more than it, then it goes to the right of it. For the sake of writing clean code, I'm not going to put it straight in here, that comparison. So I'll just put inserting a new node into another function, and then we can then call that guy here. So essentially, let's say we'll come back here in a bit. Let's say we write a function called insert new node. It's optional, but you can put it in there. But you will not be able to use this one in isolation. with this comparison to check which direction to go, check which direction to go, and insert a new node. That's basically what this our function. So we're trying to insert a new node. So the new node, to insert a new node, we have two values: the new node and the existing node. The new node and the existing node. So let's say the existing node is called node and the new node is called new node. These are param that we're passing into that function. Insert new node. So let me call it new node. Insert new node or insert node, whichever one. So the existing node is this, new node is that. So the first thing I'm going to check is if the data is less than the, so if, just like we have stated, if the new data is less than the existing node data, then go left. Go to the left. So that is, let's code that out. If new node data, we are comparing if new node data dot data, assuming this is an object, of course it's an object, dot data, which is the data down, if this new node dot data is less than the node, existing node dot data, the data inside the existing node, then we push it to the left. All right, now in the left, it's possible that is the first person in the left. It's possible that is the first. So when it gets to the left, just like in this case here, when it gets to the left, it might meet data there. So if he meets data there, he still has to go do the comparison and compare it with that, and then know which direction to go. All right, so when you get to that left, it's not default that there's a position for it, because this slot is limited. If someone is already occupying that position, you have to then check, am I more than you? If I'm more than you, I go to the right of you. If I'm less than you, I go to the left. When I get there again, I ask. This is a recursion. So this function is a recursion. It's going to be calling itself until it flattens out. So if this new node data is less than that, then we are going to check again, pretty much like what we did here. To check if it is null. If it is null, then we do. So we then check if there is data on the left already. All right, so check if there's data on the left already. So what you're doing there is just to say that if the node, which is the existing data, dot left is equals to 0 or equals to null, that is, it means that there's no data on the left already. All right, so if there's no data on the left already, then node.left becomes the new node. You set this new node to the left if there's no data. So if there's no data, I'm trying to say so that if there is no data on the left or to the left, set new data has the data. All right, already. So because we know that, of course, less lower number comes to the left. So if there's no this thing, set it as it. But if there is, then he's going to ask the question again from the number that he met there. The number that he meets there and say, guy, am I more than you or less than you? So if I'm more than you, I'm going to your right. Less than you, I'm going to your left. So otherwise, this guy is going to call it. This is going to repeat itself, pretty much like asking, the same question that you asked the first node. So else, check if there is data on the left. If there's no data on the left, right? Set new data. This thing. I think I should bring this guy inside here. If there's no data, there's else. Else, go one more time and ask the same question, which is a recursion now. So remember, recursion is a function calling itself. So when you are here, you ask, am I more than you? I'm less than you. I come here. When I get here, I meet another number. I'm going to have to ask the same question again. The same thing I did to this guy, I'm going to do to you again. That is exactly what we are saying. So when you come here, am I more than you? I'm less than you. I'll go to the left. I'll come here again. Am I more than you or less than you? I come to the left. Am I more than you and less than you? I come to the left, and then there's no data again. I stay as the left default. So that's what we're talking about here. So we continue. Otherwise, hacks continue to ask the same question. Is this, from the node, from the data that you meet there, node dot left. In this instance, node dot left becomes because you're already on the left already. So this is not just nodes now. Well, you're already on the left now. So the node on the left hand side becomes the data, becomes a node, right? And then new node here. So don't get it twisted. I'm using this guy so that it's very clear. This is the originally we came here, all right? So when you came here, this is the node. This data is less than this, and it goes to the left, right? So in this instance here, we are not talking about this node again. We are talking about the node, the left of it, okay? The left of this node, and that's what we're using here, okay? And then the same thing would would affect, even will continue to recall, it will recoil within that function, in as much as the value to the left is not null. So it begins to act, it asks the same question over and over again until you finally find its position. So essentially this is it. If the new data is less than that, then go to the left. So the next thing is we go to the right, okay? Else we go to the right. Which is here, the else of this one. Else will go to the right, okay? So now when we're on the right, we have if we're going to do the same thing here. If the node, we check if there's already the existing data. So check if there is an existing node or data on the right already, okay? If there is, so if node dot right rather, if node dot right is equals to null, if it is null, Then we have node dot write is set as that new data. Otherwise, you keep on asking the same question. New node, which is the new node, becomes the data. New node becomes the data. Otherwise, we continue to ask the same question. Okay. All right. So else, we continue to ask the same question from everybody you meet on your way. So when you get there, you ask if I'm more than you. So insert node. So node dot write, this instance becomes the de facto node. Now we have new node. Okay, so we have that. Okay, so this is it really. This is it really. So the next thing we're going to do is just to call this guy here in our inserts. This whole thing here, we want to call it here. Else this dot insert node. So this becomes this root, that's the existing node, and the new node that we have here. Okay, so if you have this, all things being equal, you have your binary tree. So for you to be able to use this, you're going to create an instance of this, and then you can call insert data. But you are not going to be able to, your implementation will not be visualized like this. Don't get it twisted. It's not going to be visualized like this. Okay, but then you can have something to it. So let's say you could have it logged into this console, into your terminal console, or we can have, so let's say we have an HTML created. Let me just create a new file here. I call it binary search 3.html. Okay, so if I have this, and then I have here, and let's say I just insert it here, src binary search tree of this. Okay, then here, let's say I want to call it in here. So let's bst or whatever variable you want to say, call it equals to new binary search tree, which is the name that you gave to that your class, binary search tree. Inside here, create an instance of this. Okay, so now we can then use this guy to insert, let's say bst dot insert. Remember that we have a method called insert, so we can use the insert the first value, Let's say the first value that we insert is 20. So 20 goes, there's no value, 20 becomes the default root. We go again, we say bst.insert. When we insert this time around, let's say we insert 26. Now when we insert 26 we'll see that okay, there's a value existing already, and that value will be 20. And then where will it go? It goes to the right because it's more than it. It goes to the right of it. If you go again, bst.insert, it will insert another value, and let's say that value is 25, or let's say that value is 18. When it comes, you see that there's an existing value, you compare it with that value, which is the root. It sees that it's less than the root, it goes to the left of it. So now we have 20, 26, 18. 20 as the root, 18 on the left, and 26 on the right. Now if you console log this, so assuming you console log this, you would see so let's say you console log bst. So you can insert more distance if you want more data, so you can explore. So if you insert this guy now, you will see that so let me go live, console.log this now. So let's check what we have on the console. Let me dispose it again. It was showing something else, so let me make this guy live server. Okay, better now. Alright, so if we check this, it was showing now. So we'll see on the console we have this binary search 3 here. So you can see there's a root node, and the value of that root node is 20. At that time there was nothing to the left and there was nothing to, so if you now check again, you have to the right, you have right node, and then you have left node. So if you check, let me see if we didn't write this properly. Yeah, so if you check that properly, you will see that you have a value 26 to the right, and then you have to the left, you have 18, to the left, like that. So it's pretty difficult for you to explore if you ask me, but if you look at it critically, you would see that it's pretty, so you have that your data pretty saved. You have that root node, the left was null, and then you have at that time the right was equally null, and then you have the right node where you have the value to be 26, right, because it's more than 20, and then you have the left node, which is 18, right, because it's less than it's less than the value 20. So this is a basic this is basic binary search. This is saving though, this is inserting. Then we'll look at finding searching the binaries, the data that you have saved, and see how fast that can be gotten. So at these junctions, I'm going to have this ended here.